everyone. Today we are going to discussing here module 3, that is transient response and arrest criteria. So in the transient response, first we shall discuss the second order system. So we know that the standard second order system, which can be represented by the transfer function T of transfer function is equal to C of S by R of S, that equals omega n square divided by s square plus 2 zeta omega ns plus omega n square. So where zeta is nothing but damping ratio of second order system, which is measured in degree, and omega n is nothing but a natural frequency or undamped natural frequency. So in general, the order of the system which is represented or identified depending on the order of s. If it is s square, it is second order. If it is s to the power of 1, it is the first order. If it is s power 0, it is the type 1 or 0 order system. So here we have to discuss the examples on second order system. So determine the undamped natural frequency and damping ratio of following second order system. So the transfer function, which is given by C of S by R of S, that equal to 4 divided by S square plus 2S plus 4. So while writing the solution, first for any given transfer function, we need to compare with a standard second order system. So we know that a standard second order system, that is transfer function equal to C of S by R of S, that equals omega n square or omega square divided by s square plus 2 zeta omega ns plus omega n square. Here we need to find the natural frequency omega n and the damping factor zeta. So just compare with standard second order system with the given transfer function. First compare the constant coefficient, that is omega n square. So that is omega n square is equal to 4. Then if we are finding the roots, we will get 2 radian per second. So then you have to find the value of, compare with second coefficient, that is the s coefficient. So 2s is equal to 2 zeta omega ns. Here 2 gets cancelled, ss gets cancelled. So therefore zeta omega n is equal to 1. Then zeta is equal to 1 divided by omega n. So we know that the value of omega n, which is equal to 2 radian per second. So hence we will get the zeta is 0.5. So next similar type, the next problem. For the second order system described by the closed loop transfer function T of S, find the value of omega n and zeta. So we know that transfer function is given by C of S by R of S. So then here we have to take the common term. Why? Because the every second order or quadratic equation must have the constant coefficient which is equal to 1. Here you have to maintain the constant coefficient must be equal to 1. So to maintain the constant coefficient equal to 1, here constant is 4. If you are divided by 4 means this s square coefficient become 1. Hence you have to consider 4 as the common factor and divide the whole denominator polynomial by 4. So here you will get 4 divided by 4, it is 1. So 12 by 4 means it is 3, and 256 by 4 means it is 64, and 4 by 24 means 4 6 the 24. So we will get the revised transfer function. Then you have to compare with standard equations, that is s square plus 2 zeta omega ns plus omega n square. 2 zeta omega ns plus omega n square. So if you are compare with constant coefficient and s coefficient, first you have to compare with constant coefficient, that is omega n square equal to 64. Then omega n, take the root of 64 is 8. Then 2 zeta omega n is equal to 3. So zeta is equal to 0.8. And if it is k into omega n equal to 6 means if you substitute the value of omega n, so we will get the 0.75. Okay. Similarly, I will get the next problem. So in this second order system, if you are knowing the standard equation, then you have to find the roots. So just if the problem will be given the only transfer function, how to find the roots of characteristic equation. So to find the roots, first you have to write this denominator polynomial as it is. as for the given function. Then you have to split this denominator as two variables. One is the S1 and one more is S2. S1 is the first constant variable and S2 is the one more constant variable. So then if it is the equation will be a minus b, that is x minus a and x minus b, means you have to apply the roots of quadratic equation. To find the roots, you have to get the equation minus 2 zeta omega n plus or minus, that is nothing but minus b plus or minus under root b square minus 4ac. Okay. So using this equation, you have to find the roots of characteristic polynomial equation. So then you have to get the conditions for second order system. So there are the three different cases or four different cases which are studied in this damping factor. So the first case is if the zeta is greater than 1, the system is overdamped. If zeta is equal to 1, system is critically damped. If zeta is less than 1, the system is underdamped. And if zeta is equal to 0, that is damping response is equal to 0. Then those cases which are mentioned in the graphs. So overdamped response, so zeta is greater than 1. You have to represent, find based on the roots, you have to mark the poles in the j omega axis. So then similarly for the same zeta value, you have to consider one problem. Calculate and the plot the output of the system following transfer function. So transfer function is given. So then you have to calculate the output response. So output means C of S. C of S is equal to R of S into T of S. R of S is unit step input, that is 1 by S. So this equation, if you are rewriting, that is apply the partial fraction. So we'll get the equation will be like this. So then the total response for the given system, if you apply the Laplace for this given equation, 1 by s means e to the power s, that is 1 plus minus 2 is the constant. 1 over s plus 1 means we can write as e raised to minus at, or plus 1 is the constant, e raised to minus 2t. This is e raised to minus 1 into t. So that will be written here. Okay, 1 minus 2 e raised to minus t minus e raised to minus 2. So while writing the exponential response for the given function, we can write like this. Okay, the zeta is greater than 1. Then for second case, if the system is critically damped, so find the roots, the only the real roots which is lies in the left half of S plane. You can call it as this is LHS, left half of S plane. You have to mark the roots. So for the same case, you have to solve the one problem. Calculate and plot output of the system for the following transfer function. So this is the transfer function which is given. So to find the output response, you have to use C of S. C of S is the output response. So if it is unit step means you can add that 1 by S. 1 by S you can add it. Then you have to rewrite the equation. Finally we will get the equation and you have to write the graph. For underdamped case, find the roots and you have to plot the graph. So the graph will be appear like this. This graph, which is called as a time domain of second order system. This is the second order graph, second order system. Here we will get the different parameters: rise time, peak time, settle time, maximum peak overshoot, and delay time. So fourth case, for undamped system, same procedure you have to follow it. Mark the poles j plus or minus j omega n means plus j omega n will be here, that is plus j omega n, and minus j omega n which is appear in the negative quadrant. Okay, so we'll get the transfer function after applying the Laplace. This is the different damping factors and we will get the response of the system for variation of output with respect to the time period. So here you have to consider the time domain specifications. That is nothing but different parameter which are described here. So first you have to plot the graph C of t in y-axis and t in x-axis. Okay. So here we will get the different case, that is delay time, rise time, peak time, settle time and maximum peak quotient. So this parameter you have to define in the next step. So the first parameter is delay time. Delay time is the time required for the response to reach its final value at the first time. So during the first time it will reach us the final value, delay time. So it will be marking as it reaches 0 to 90% of maximum value. So that is called as delay time. So it is the time required for the response to reach half of the final value in the first time. Okay. So then the second parameter is rise time. So delay time, which is given by Td is equal to 1 plus 0.7 zeta divided by omega d. So delay time, which is mathematically represented as 1 plus zero point 0.7 zeta divided by omega d. Okay, this is the equation for finding of delay time. Then rise time. Rise time is, it is the time required for the response to reach its 90% of full final value. So 10 to 90%. So suppose if it is a 10%, it is 0.1 and this is 0.5. So delay time is 10 to 90% of final value, which is called as delay time. Sorry, rise time. So this rise time, which is given by the equation Tr is equal to pi minus theta divided by omega d. So theta is nothing but tan inverse of omega n divided by omega n into under root 1 minus zeta square divided by zeta into omega n, or omega n into root of, you can write like this, omega n into under root 1 minus zeta square divided by omega d, or 1 minus zeta square by zeta. So there is a small correction. Okay. So theta is equal to tan inverse of omega n into under root 1 minus zeta square divided by zeta. Then peak time. So peak time is given by Tp is equal to pi divided by omega d. So it is the time required for the response to reach first peak of overshoot. So first peak of overshoot means this is the point, that is first peak of overshoot. It starts from 0 and reaches the maximum peak value, that we can call it as peak time. Okay. Next, maximum peak overshoot. So it is the maximum peak value of a response curve measured from the unity. This is defined as follows. So the maximum peak overshoot is nothing but the time required for the response to reach from 1 to maximum peak value, that is from 0 level or reference point to the maximum peak value. So this maximum peak overshoot, which is given by e to the power minus pi zeta under root divided by under root 1 minus zeta square. Okay, this is the parameter description for maximum peak overshoot. Then you have to find the settle time. It is the time required for the response curve to reach and stay within the range about the final value of specified percentage of final value, or else final value. Here you will get the 2 to 5% of tolerance. That is nothing but allowable tolerance means while settle down the complete response curve, so small disturbance or small variation of time period. So 0.02 or 2 to 5%. So this is the nature of curve for the settle time or step response curve. So settle time, which is given by Ts is equal to 4 divided by zeta omega n. If it is for 5% tolerance, so Ts is equal to 3 divided by zeta into omega n. So let us discuss with problem on the time domain. For the control system shown in figure, determine the value of k that satisfy the following requirement: maximum percentage overshoot or peak overshoot, and settle time is 1 second. Using these two data, we have to find the value of k. So this is the transfer function. So these two blocks in series, and this is feedback. If you apply the feedback and block diagram reduction technique, you will get the equation like this. If I rewrite the equation in the standard form, k divided by s square plus s into a plus 2 plus 2a plus k. So peak overshoot is given, that is 0.6. So 110% means that is 10%. We'll get 10 by 100. So we'll get the 0.6. Sorry, 10 by 100. So from this equation you have to find the value of zeta. Then settle time is given. Ts is equal to 3 divided by omega d. So that is settle time is given 3 divided by zeta into omega n, that equal to 1. So omega n is known. So zeta is known. You have to find the value of omega n. So we get the equation. So then after finding the value of omega n and zeta, we'll get the value of a and k. Then the higher order system. So higher order means more second order. The natural response of higher order system consists of sum of the term, one term from each characteristic equation. For each distinct real characteristics root, there is a real exponential term in the system of natural pairs. So for each pair of complex conjugate, if roots are complex conjugate, then the nature of response curve is exponential, sinusoidally exponential. If roots are repeated roots, then the total response curve is natural exponential curve. Okay. So this is the problem. We have to discuss the first problem, problem number 1. Analyze the system with the following transfer function. So this is the transfer function. So this equation can be rewritten as polynomial equation s plus 1 s plus 4 into s square plus 4s plus 30. So with unit step input, apply the partial fraction and you have to find the response. Okay. So this is c of s is equal to 1 by s into t of s. So apply the partial fraction and find the value of zeta and omega n. Okay. So if you are applying that, then you will get the value of omega and you have to plot the curves. So this is the underdamped case. This is the damping factor. This is the exponential. This is in j omega axis. These roots of characteristic equation, which is lies in real and imaginary section. Okay. So let us discuss with one more problem. Consider the system shown in figure where damping ratio is 0.6, natural frequency is 5 radian. Obtain the rise time, peak time, maximum peak overshoot, settle time, and find which is subjected to unit step input. This is the given transfer function or given block diagram. Reduce the block diagram into standard form. Then you have to find the value of corresponding coefficients. So here the first parameter we need to find is rise time. Rise time is given by pi minus theta divided by omega d. Theta is equal to tan inverse of omega n under root 1 minus zeta square divided by zeta. This is not omega n. Okay. So this is comes under root. So we will get the value of tan theta is equal to 0.93 radians. So then rise time is equal to pi minus theta. So pi minus theta is here. Zeta is known. We will get the rise time. Then to find the peak time, Tp is equal to pi divided by omega d. So Tp, peak time is known. So pi is 3.141 divided by omega d is 4. So we get the answer. Then you have to find the settle time. So settle time is given 2%. Settle time is 2% means you can use the standard formula 4 divided by zeta into omega n. Substitute the values, you will get the settle time. If it is settle time is 5%, you will get the Ts. Then to find the maximum peak overshoot, you can use this formula and you will get the maximum peak overshoot. Similar type, we are discussing the next problem. For the system shown in figure, determine the value of gain k and velocity feedback constant kh so that maximum overshoot in the unit step response is 0.2 and the peak time is 1 second. With these values, obtain the rise time and settle time. This is the complete block diagram. So first we have to apply here elimination of blocks. Then we will get one block. So blocks in series, again elimination of block. So that will be done here. Look at the block diagram. So we'll get the final transfer function. So from this transfer function you have to find the value of kh. So compare with standard equation. This is not necessary. Okay, first consider the constant term omega n square equal to k, omega n equal to root k. Then compare the s coefficient. Here s coefficient is 1 plus kkh. So 2 zeta omega n is equal to 1 plus kkh. Zeta is equal to 1 plus k into kh divided by 2 root k. So then omega n is equal to root k. This is zeta. So in that problem they have to give on the maximum overshoot. Using this maximum overshoot you have to find the value of zeta. So maximum peak overshoot is given by mp is equal to e to raise to minus pi zeta divided by under root 1 minus zeta square. So if you are solving the equation you will get the zeta value. Then peak time is given, that is 1 second. From this peak time you have to find the value of omega n. So where omega d equal to omega n under root 1 minus zeta square. So we'll get the omega n. From zeta and omega n, you have to find the value of corresponding constant, that is k and kh. Okay. So then if you are using this equation, you have to find the rise time, settle time. So similar type, the next problem. When the system is shown in figure, which is subjected to unit step input for the system response as shown in figure, determine the value of A and C from the response curve.